So we're talking about advanced sheet metal today. The agenda I want to go through on this, though, is kind of an interesting way to approach advanced. The word advanced in CAD terms, people always think complex, or when it comes to a shape, a very organic shape. And when it comes to sheet metal by nature is actually advanced in just what it's doing. So I want to talk a little bit about what's under the hood a bit, and then some ways to set your system up in an advanced way that's going to help you quite a bit. Things that people should be doing but often don't do, frankly. We'll do a little bit about advanced shapes because that's always necessary, and the features that are used to control those. And we'll talk a little bit about flattening, because that is the magic bullet of sheet metal. It really is a different type of geometry in SOLIDWORKS than other things, because it has a life in a flat pattern as well as a folded, and then very many configurations in between. So again, it's a very unique type of thing. So really, what is sheet metal? Now, sheet metal is one of those terms that we use, but the fact is, it really just defines thin materials. We can use it for a lot of different things. People with corrugated cardboard use it. It's all about how you calculate the bends. And of course, metal is going to fold and bend, where corrugated cardboard technically collapses in on itself in a bend. But if you use the proper calculations, we can go ahead and get a nice flat pattern that's going to be quite accurate. What's really happening, though, is that we're mapping cylinders to a plane. So when we talk about sheet metal, what we're really talking about for the most part is linear bends. That's always been the traditional thing. So we're talking about things like this box here, where things fold over and flaps collapse on themselves, and there's tabs and other types of features. But we're really taking these bends here and just mapping them to a flat pattern. The common features that are typically used will make a part like you'd see here. A lot of bracketry and enclosures and the things that you're seeing on the floor and on the wall here. I think fog filler uses some sheet metal, but I'm not, well, it's pretty obvious what kind of sheet metal you're using here. Now, sheet metal, again, is a couple of different things when we talk about it. Fold unfold is traditionally what the CAD approach is, and these are the kind of features that you'd end up creating here. So flanges and hems, and in this particular case, we're just using a lot of corner breaks, but it's a lot of very repetitive stuff when it comes down to it. Base flanges are pretty common. Again, these types of brackets are the things that you would use quite often. But the calculations that we're using to create these parts are the difference between an okay part with pretty loose tolerances versus an ultra accurate part, which some people do go for in these scenarios as well. So let's get into the first part about this. What's so advanced about what I just showed you? Well, the reality is what's happening here is some pretty funky stuff under the hood. And to really make your sheet metal parts accurate, it really bears to understand this a little bit better. So when we're talking about the way that we calculate these things, the K factor is generally what we're talking about, but there's two other areas called bend allowance and bend deduction that are used to calculate how we determine the difference between a folded versus a flat. And I'm sorry I'm doing hand puppets up here, but folded versus flat versions of a part. Because the reality is when you go ahead and apply these types of calculations, you can change this based on just, again, tweaking these numbers. And your part will be different in a linear bend when it's folded versus its flat pattern. It could end up being longer in the flat versus shorter in the flat, depending on whether there's tension or compression as the primary component inside of your bends. So when we're talking about these types of things, we're talking about trying to get your machinery predictable and your parts coming out of the end of the machinery, again, in a predictable size. And the point of this is that I'll show you how these calculations work, but there's a lot of examples that come with the SOLIDWORKS software that are just examples. For example, we don't provide you with an accurate bend table to use for your parts. We give you an example bend table. And the reason is generally because it's based on how people process things. So when we're creating what I'm about to show you here when it comes to these bend tables and K factors, a lot of times there's a little trial and error in the beginning to where you take a known part and build it in 3D, measure it in 2D, and then use that to kind of reverse engineer what your calculation or your K factor is based on how your machinery works, how your press brakes work, or if you have CNC tools. There's a lot of variability when it comes to sheet metal and a lot of looseness when it comes to the tolerances typically as well. So the K factor. This is generally a number that is put in as you create sheet metal, and it again determines whether the part is the same linear length flat as it would be folded, measured on the midplane, versus longer or shorter, again with tension and compression in each of those corners. Now, this is some voodoo here, that the graphics that you're seeing here, this is just in the SOLIDWORKS help file, so you can find these particular graphics here. But it has to do a little bit with the end side radius, the actual arc angle itself, and then this thickness value here happens to be the distance the midplane is from the inside of the part. So what we're really talking about on something like that is the neutral plane that's used to calculate this. So no matter how thick your sheet metal part is, it really is an infinitely small surface that is being calculated to fold and unfold at. It's where this neutral plane happens to be. The default is always 0.5, which is right in the center of the part. And what that tells you is that it will be a 1-to-1 ratio. Measure your part through the center here will be exactly the same length as if you unfold it and measure one long edge. So that was where 0.5 comes in. Ooh, I'm not sure what that means. Okay, that's exactly what it means. Good. So we're really talking about this neutral plane. I'd say 98% of the people we deal with just plug in a K-factor. Now, this is where things kind of get interesting, because when you're talking about a K-factor of 0.5, you're basically talking about a mid-plane right down the center of the part, as we would see here. But what happens when your part isn't a U-shape and it's an S-shape? And you start to change where that K-factor is, more inward or more outward. So what I'm getting at is that if I do a K-factor of 0 versus a K-factor of 0.5, that actually makes the neutral axis the inside face of the part, okay? So on an inside of a bend, the length is actually going to be much shorter because it will essentially, as it unfolds it will compress this outside bend so that it actually flattens and has some, in real life, some wrinkling, some oil canning, some other sort of bunching in those corners. Now I'm going to pull up this part here for a second because what I really want to do is kind of just show you a little overlay that actually shows how this thing is calculated. So back in SOLIDWORKS here for a second, if I could, we're going to go ahead and pull up these two parts, and I just want to illustrate this with a little bit of a sketch overlay that we've got here. So when we're talking about calculation, I want to look at the U-shaped part here first, just as my example here. When we're talking about a K-factor of 0.5, what we're really talking about on something like this is a sketch that is essentially right through the center of the part. Now if that K-factor moves towards the middle, what you're talking about now again is calculating the length of the part based on where this plane is. So in this scenario, the part flat will be shorter than the part that is folded up. Now if the K-factor again is 0.5, you're talking about a 1-to-1 ratio. It'll be exactly the same flat as it is folded. And then again to the outside, now you're talking about some compression on the inside and some tension on the outside, but it's a different ratio to those. Now what I was concerned with initially when I talked about K-factor being set to the inside, for example, is when you're talking about the inside bends here, it concerned me when we got to a part that was S-shaped. And the reality of it is the software knows enough to know that it's going to calculate the inside of a bend regardless of what direction that bend goes. So in other words, the straight sections here are going to be calculated as straight, but if we had this K-factor set to 0.1, it would be inward on this bend and inward on this bend. So effectively the sketches that you see here is what actually gets measured. So I was concerned once upon a time that it would actually do a line on the inside, and then as it went around this direction, it would also be on that predominantly right side versus left side of the part, so over here. So when you set your K-factors, the basics again, once again, is that if you go ahead and start unfolding your part, it will change that length relative to the folded version of it. But it's all based, again, on processing equipment. So a little trial and error will go ahead and nail that to get the accuracy of your processing. When bend calculations are upped a bit, there's more factors here, but again, it leads to a little bit more ultra accuracy. We start to calculate things using the bend allowance or the bend deduction. Now, what it comes down to is a K-factor. That's the number we're still going to find, but it comes down to a K-factor that is so granular that based on the radius of an edge, the thickness of the material, and said angle, it will be a different K-factor that it gets used to calculate each individual bend of a part. So if you had a super complex part that had 50 bends and there were different radiuses and all different angles, theoretically each one of those bends will be calculated with a different K-factor using a table like this, because it would find everything that's a 16th and everything that was a thickness of the part that was whatever the thickness is, it would take those K-factors and essentially, I'm sorry, I'm scrolling through, it would essentially go ahead and roll those K-factors based on the different radii that are there. And when you're talking about forming equipment or press brakes, you're talking about very tight wedges versus very loose and round, and that's again a difference in tension and compression. But these are where companies up things when they want to get that ultra precise thing. You're not just using one number of a K-factor, you're using an individual unique number for every nuance within the part. And those again get incredibly granular. Now as I mentioned before, these are things that we provide with the software as an example, and I'll show you where that is. Because the gauge table is another thing that we also provide as an example, and they both kind of live in the same spot. Gauge tables are something that I would implore everybody to use. Bend tables, again, that's based on the accuracy that you need. A lot of people make sheet metal parts with larger holes or with slotted features so that they do have that variability on fit up. But what a gauge table actually does for you is it changes your SOLIDWORKS interface. And it only allows you to select these particular values as thickness of material. So you go ahead and fill this out with material you keep on hand. The radii, which would be the tools that you have available to you. And that's so somebody who's designing a sheet metal part isn't just keying in numbers out of the blue, right? You've got to make custom tools to be able to go ahead and make custom radii. But if you use a gauge table like this, what you're basically doing is changing the SOLIDWORKS interface so that pull-down menus appear and users can only choose the gauges that you've determined. Now I'm going to go backwards one on this for a second because I've got a little hyperlink here that takes you to where this is. Now your install directory is going to be different than where mine is. So mine happens to be, and frankly I've been doing this for a long time on this laptop, so the gauge tables I'm referencing are actually a SOLIDWORKS 2019 folder, even though I'm on SOLIDWORKS 2022 right now. But what it will do is it will take you to your SOLIDWORKS install directory, which is generally program files, SOLIDWORKS, a localized version potentially, or SOLIDWORKS Corp will be yours. And then we end up getting into, give me 1 second here. And then we get into language and English, because everything is going to be localized. So when you get under your sheet metal gauge tables here, and this will be what your full path actually looks like, what you're looking at is just Excel spreadsheets. And any of these gauge tables, again, can simply be double-clicked. Go ahead and open it up, make changes to it, and then just save it as any old name. And these are something that we can point to when we're actually, again, defining some sheet metal features here. So at this point, I'm looking at a gauge table where I would only be able to select thicknesses, once again, that are on hand. Those gauges are just corresponding to a number. So if you don't know the millimeters or inches number of a gauge, then you just go by that general value. But then the pull-down menus for the radius are actually going to roll based on what the selection of the gauge happens to be. And it will, again, only select those types of radii for input, not just any number under the sun. So those things are incredibly important when it comes to the consistency of how people design things, again, based on what you can do manufacturing-wise. So once I get some other parts up here, I'll go ahead and pull up where the gauge tables are, and you can see exactly how the interface does change as a result of that. Okay, an advanced feature that you should be using if you don't is called the design library. In this particular case, design libraries for a lot of areas in SOLIDWORKS, but for this one it's called our forming tools. Now the design library is pretty important because it allows you to have repeatable things for stamping tools that you would have in a turret punch, for example. Many companies will process sheet metal by putting it in a turret punch, and it either nips off a bunch of things with straight features, takes coining operations, punches out tons of holes, or even stamps in things like louvers and embossments and those types of things. And these types of stamping die features are something that you can create for yourself. The beauty of them is that they represent the male half of the stamping die, but you can drop it on any thickness of sheet metal material, and as long as the radius that's in the part matches or will work for the thickness of material you're using, then things will function properly. So in other words, if I have a very small stamping tool and I'm putting it on 1/2 inch sheet metal, it's probably not going to work because I don't have enough radii to stamp that out. And we have had customers that have 1/2 inch sheet metal, by the way, and up to 1 inch actually, in military applications. So it's pretty impressive to see that. But the process of it is something that is very open-ended for the individual user. And what I mean by that is you can create your own very, very simply. And we implore you to do that because we want you to have whatever tools you'd have on hand in a typical manufacturing operation. Now, what these things do for us really simply is, again, provide repeatability to the stuff we use all the time. When you're in a sheet metal part in SOLIDWORKS, it's the library books over here on the right-hand side. So you basically just go ahead and tap that little set of library books, and it's got all kinds of other things in the SOLIDWORKS default directory as examples, which is a great thing to use. Once again, this is going to be based on one of your SOLIDWORKS install directories. Mine still might be, pointing to 2019. But it gives you a bunch of examples of little assemblies, features that you can drag onto your part, like keyways and slots. Again, anything can be modified and used for your own purposes. But then there's also these forming tools. Now, what's interesting about what you see here, first of all, is you can see obviously the folder looks a little different for each of those. The only difference between a folder with forming tools in it and a folder with parts in it is that somebody right-clicked on it and actually triggered this little thing called I am a forming tools folder, same as the one with assemblies. Because if you see this one right here, I right-click on it, you'll see there's a check mark right there. Because the reality is the things that are consuming this particular folder, if you were to open them up by a little right-click, these are no more than part files. They're just a part file. But it has to know when you're dragging it in that you're not dragging a part file into another part file or an assembly. You're actually dragging in a sheet metal forming tool. So what we have here is nothing more than a regular part file that was built up in a particular way, and I'll show you one of these in another way here. This is one from the training files that we've got. But this enables us to go ahead and take this little forming tool and have something that I can very, very easily just go ahead and drag out onto my part. So these forming tools are wonderful because as I go ahead and grab them and drag them in place, you get a wonderful preview of what it looks like on whatever face you're putting it on. The tab key allows you to go either inward or outward with the preview. And once you place that feature, it's a lot like a hole wizard component, where even in this case I can flip the tool if I want to. But if I need more than one, there's a positions button up here at the top that'll enable me to go ahead and add additional points. You can either do this ahead of time or after the fact, but it just allows you to go ahead and put these in quite quickly. And they actually create an embossed or an indented feature in the part. Now, not only that, but it also removes a little bit of this little face on the inside. Now, the way that I just created the one that I showed you right there was basically an automatic function within the software. You build up a feature that just has to represent what you want to be the side that's removed. So what you basically see here on the screen again is just a basic series of an extrusion, another extrusion, and this feature down here on the bottom, by the way, is only so we can get that fillet to go outward. If that wasn't there, of course, the fillet would go around the other direction. And then in this case, I put a fillet on the top and a little feature here for a split line. That split line allows us to designate an area to actually get removed. So what you do is you go to your sheet metal tools here. It's a little button up here called Forming Tool. Now it walks you through the process, and actually couldn't be any simpler. It's asking you for a little feature here called a stop face. Ooh, excuse me a second. Not sure if I can actually hit that one since I've already got a form tool built into this one. Let's kill that. You see the colors that are there, they're done by the way that you select things. So when you start with a forming tool, it's asking for two things. A stop face, which is when you stamp it, where does it stop when it hits the part? So what that designates really is this face. The rest of this would be part of the embossed feature. Faces to remove will simply dictate something that's going to go away. So if you do have some sort of, on the real stamping die, some sort of cutting feature or edge, that'll dictate where something gets removed. So you just select that. Now when you do that, it's going to give you a nice little color-coded feature. Anything that's yellow will be embossed. Anything that's the blue area there, that's the stop face, so that's going to stay out of the part. And anything that's red there actually gets removed. So there's a lot of different ways to do that. And you know, I actually had a different file set up to even show you how to do this, oddly enough. That's really the process that it takes to go ahead and make any one of those your own. I'm going to try and find my own one here. There we go. So same kind of thing I was talking about. And again, build it any way that you want to. But the main thing is the radii that are sitting in here have to work for the thickness of the material that you actually put in there. So when you do go ahead and run through that basic process here, I'm going to take a little longer on this one because I want you to see what this looks like. But I'm going to use a removal feature here where I actually select a series of faces. Now because of the geometry that I've created here, my right click select tangency doesn't seem to be there. So if anybody's asking in your head why Darin isn't doing that, it's because it doesn't happen to be there. But based on this, it's really worth the work that I'm about to do, because essentially all these faces that I'm selecting on the inside are going to be the stuff that gets ignored or removed. Now geometrically, what's interesting about this is that the part you're looking at doesn't really have the geometry that would be necessary for that cut. There would be a protrusion that would have kind of a knife edge to it, and it would actually slice these areas out. But as far as this feature is concerned, it just has to be designated in this red 255, green, blue, 00 color in order for this to actually work. Now, once this is done like this, what you're basically doing is just dropping it onto the other component. And for this particular one here, we're just going to go ahead and drop that into a particular spot, and it will give us this embossment. So the beauty, once again, is you can make anything that you want here. Oh, shoot. Give me a second here. Sorry, pilot error. I'm using two different ones. There we go. When you're dragging this thing out, what you'll get is that beautiful preview once again. So as you drop this onto a face, the tab key allows you to go inward or outward. And once that's in place, really it's just a matter of either dimensioning this feature if you need to. Sketches will allow you to go ahead and dimension that with the position tool, or you can go ahead and add additional ones through, again, clicking additional points. But placing that is no more than just dimensioning sketches. The result of it all gives you this wonderful embossment. Once again, it's going to go ahead and take the thickness, and it will take the radii and roll those up as if this forming tool that we had sits right on the inside of this cavity. So again, whatever that thickness is, it grows independently outward from whatever the form tool happens to be. So put those in your library, and it's basically work on it once, get it done, and from there, it's all just drag and drop. Pattern features, mirror features, all of those do support this type of tool. So drop one in, pattern it at will, mirror it to the opposite side, and keep rocking. Any questions on that one?
Yeah. If you insert one in, do they maintain their parametric constraints? Like if you change it, will it change in every file?
That's actually a fantastic question. I did not mention that, and I had meant to mention that, so appreciate that. There is an option with that. Like with everything in SOLIDWORKS, I've been doing this a long time, and I'm a demo guy, so there are some things that are very, very much demo-y, and other things that are reality. One of the awesome things about SOLIDWORKS, of course, is that if you change a part, it changes everywhere it was used. One of the horrifying things about SOLIDWORKS is that if you change a part, it changes everywhere it was used. And that's where data management comes in, because that can throttle that process. But when I drop this form feature in, you will notice not only here, but in a lot of places in SOLIDWORKS, you end up with this little option over in the feature tree called Link To. Now, if that check mark is left, and I go into the library, I open up and edit that tool, everywhere it was used will expand or it will contract. So this turned off, this check mark to the Link to Form tool. If I turn that off, this is more or less a copy. If I leave it on, it is very much associative to the feature in the said folder that I dragged it from, which again, can be awesome or can be horrifying, but when you're talking about standards, standards generally don't change, right? Or if you're talking about these standards are something you very much have your thumb on what's going on with them. There's not something that's changing, for no good reason. So I like to have these things linked. But yeah, absolutely 100% associative there. And that's part of the whole arc where this is a part file still. And it's a part file that's referenced by another part file as a result of our little telltale external reference arrows there. So that would actually turn off right there had I turned that link symbol off as well. All right, good question. Very good question. No matter what happens though, I've dropped it on a face, and hitting flatten, it just lives on the face that you've dropped it on. So no voodoo to make that happen. It will stay put and it will go in position. We don't take the formed features into account when calculations are done though. I know in real life there's probably a little stretching or a little bunching or thinning in these areas because it's grabbing material and it's pulling it into other spots. There's a little bit of stuff you have to kind of suspend disbelief on, but in these particular respects, it's not really germane to the geometry there, and it's going to be something that's just easier to do in a repetitive process. Customize, good, okay. One of my favorite features here is called Convert to Sheet Metal. We have a dozen things for creating complex corners and extending things and doing all these really weird merges to get very, very complex multi-angle, compound angle parts. But this feature is really the magic to create, in the easiest sense, some of the more compound hoppers and other parts that just have several angles of crazy edges coming together. And the feature kind of speaks for itself, so I'm going to go through it here. Convert to Sheet Metal really simply is just taking a normal extruded part created with normal features, and then sort of shelling it to create it into a sheet metal part, if you want to just use very simple terms for what our tools do. For this particular process though, it gives you some incredible flexibility. The second one I'm going to show you here would be a situation where we have it's a milled part. It's a milled part that could be very heavy, could be very expensive depending on the material, and it might just not be worth it based on making it as a machine part, where making it as a sheet metal part in a box bracket or something to that effect might be much more cost effective especially, but lighter in the design. And that's where you can kind of pivot mid-design in order to do this. So let me show you what I'm talking about when it comes to a Convert to Sheet Metal feature. So this one here is my favorite because, again, it takes a lot of the disciplines that even seasoned sheet metal people had. And when this was added to the software, it even expanded some of the most seasoned users' capabilities for what they could make. What I have here is essentially a hopper, okay? And that hopper can take a lot of different forms. But to make this from sheet metal features, it's actually fairly difficult because it's not straight edges. There are a lot of straight edges, but then those edges have to be extended and overlapped. And there's just a bunch of features that you can make it that way. But it really is much easier to make this geometry by just doing what we have here, which is essentially a really simple extrude. I believe it's an extrude from the side shape there if I show you the sketch, right? Basic extrude, Then we went ahead and took that extrude and added some draft to some of the faces. And then we did a cut. That just slices right through here. Then there's another cut from the side, and that slices the bottom off on an angle. And now we have compound, compound, compound angles. Well, I want to make this a sheet metal part, and I want to do it in a very simple process. So again, the magic bullet is this wonderful button called Convert to Sheet Metal. Now, if you've been using SOLIDWORKS long enough and your software has been installed since before Convert to Sheet Metal existed, this could be with any feature, frankly, more times than not, your IT installs new versions of SOLIDWORKS by inheriting the toolbar settings from your previous version. Most of you want the tools and options and hotkeys and all that other stuff the same. The rub is that new buttons in the new version aren't going to show up with your old toolbar settings because they're simply not aware of it. So when you find something like Convert to Sheet Metal or a tool that you use rarely, I want you to use this tool up here called Commands Search to go ahead and help yourself out. Generally, by default, it's going to be a file search tool. People really kind of stay away from it because all they see is this little thing up here called SOLIDWORKS Files and Models. Nobody does that. But you might come up here and hit the Commands Search button. And what happens when you hit Command Search is you have the ability to type in a little bit of a command. So if I go ahead and say CONV, what I have is convert cut, convert to extrusion, convert to mesh body, convert to sheet metal. So it basically gives you the wildcards of what those words match. Now I can run this button here called convert to sheet metal if I want to, but what I could also do is I could run that little guy right up there and I could just drag it over to my toolbars and actually put it on your toolbar here so you can use it next time. So that's a little special one right there. I love doing that. Drag it to your toolbar. If not, you just want to use it once, you can just go ahead and run it just by clicking on it and hitting the button. Or hit the little creepy eyeball and it will actually take your cursor and it will show you on your interface where your button actually is. So it took my cursor and it jumped it over to where that button was actually over on the left-hand side, not this one that I added. Another little side benefit, if you have too many buttons on your toolbars, this has nothing to do with sheet metal, but you don't have to go into all of the customizing tools to get rid of those. Just hold down the Alt button, pick and drag it off the toolbar, and it's gone. Okay. So any buttons you don't like, just go ahead and hold down the Alt button and pick and drag those off of there. Okay, so back to where we were. I get a little sidetracked. Convert to Sheet Metal's workflow is very, very simple. Now, what you see over here on the left-hand side, first of all, is I haven't really shown you much with the gauge tables we have there, because right now I can type in any thicknesses I want. I can type in any radius that I want. But when you go ahead and trigger this Use Gauge Tables option, what ends up happening now is that it's going to take all of this interface and it's going to get rid of it. It's going to turn it into pull-down menus. So it takes a few seconds to do this because it's embedding this Excel spreadsheet into the sheet metal file. That way if I send it to any of you, you've got my spreadsheet, so it all works. But now what I have for sheet metal parameters is a list of pull-down menus that I had before. And from each of those little gauges, what we have is a list of very discrete radii. And that's what a gauge table does for you, so it's pretty awesome. I'm actually going to turn that off right now, but I just wanted you to see what that looked like. Okay, so what we have right now is a sheet metal part. So the process is just like other sheet metal parts, is you want to pick a stationary face. Once we do that, what it does is it fires up the preview. So you can see that there's a thickness here that's available. We can go ahead and start messing with that if we need to. And then again, a radii that's available if we need to deal with that. What also is awesome about this is it's very smart. So as I continue to incorporate additional edges and faces, it will automatically know what to do with those. So here's my first face. We're going to start with that. Now I'm going to pick this edge between the bottom face and this back face. And by picking that edge, it automatically brings that face into things. Okay? If I leave it as it is right now, this is what we get. Okay? Really simple, but very quickly it created something that looks like this, which is a really great flat pattern for something I didn't want to make manually. Now I'm going to go back and edit that Convert to Sheet Metal, which is going to leave me right where I was before. And again, what's beautiful about this is all we're doing is selecting a bunch of edges to bend. So as a result of that, what I could do is I could select this edge and it will incorporate this flap. And I could select this edge and it will incorporate that flap. But more importantly, it also grabs these little edges down here at the bottom. And because this edge is a bend and this edge is a bend, these two edges can't be a bend. They have to be able to separate. So it automatically puts it into this folder called RIP. So as I select adjacent faces, you'll notice it automatically does all of this. If I grab this edge here, you'll see that down there it has to incorporate a RIP. If I grab this edge here, it has to incorporate a RIP. So we're really just grabbing all of the edges we want to make these bends, and that's going to go ahead and additionally put in all these flaps. Maybe we'll do that one right there too. Oh yeah, see, vertical edges right there. Now, if I wanted to keep doing this, I could keep the body active and make other features. I'll do that next time. But what I've just done is I've converted this into a sheet metal part, which now with a flat pattern is a pretty elaborate flat pattern. And that's just by picking the edges of an existing part made with a couple of extrusions and cuts. So that will make a very nice watertight body of this really wild hopper. Now, I told you that we'll go a little bit different with this when it came to a machined part. Machined parts are interesting because, like I said, this thing's got holes. It's got parts that are going to have to bolt up to it, and it's going to bridge the gap between a couple of other parts. But right now it's pretty heavy, and it's going to be a big billet to create this and a lot of chips. So it's just not the best really approach for a part like this. But if I decide at the 11th hour that I want to go ahead and convert this to sheet metal, I can do that. Now again, it's the same process. You pick the face to remain stationary, and it instantly starts to preview. That's a little bit thick for what we're going to do here. And then once I start to grab other edges, it's going to automatically put those faces that those edges are part of in this particular selection set. So I just kind of keep an eye on it. I do the side flaps there, so maybe that's going to give me what I need there. Maybe we'll do a little front flap and top flap up here. That's kind of fun. Maybe a little front flap on that one. And again, we can just kind of grab different edges and incorporate things as necessary. Now, it will get mad at us at a particular point if we ever have a situation where this part, which looks pretty good in 3D, is going to collapse back onto itself when it unfolds. So it's not yelling at, ooh, it is yelling at me actually right there. Warning. So bends intersect multiple faces are fused together. Okay, whatever. We're gonna see it unfold here. Do we see it hit itself? Yeah, it's actually going to collapse back onto itself, which means it's not gonna show me the flat pattern. So right up in here, because of things and the way they're gonna unfold, we're basically gonna end up having a couple of edges that share material, and you can't cut those apart and do that in a 3D. So the software is right now yelling at me a little bit on exactly what I've done and why there's a problem there. So that's okay. SOLIDWORKS being 100% editable, I can always go back and start removing edges out of some of these bends if I want to and vet this part a little differently. But that flexibility is incredible, and it does allow you to not only come in here and make, you know, a single component from this, but if I was to go ahead and leave that component intact and leave the actual solid body there, we can do multi-body with all of this as well. So a little check mark up here called keep body.
Recording region indicator.
Keep body will actually go ahead and create the unfold that you see, but it will leave that little solid body there so that I can make a second feature if I wanted to. So again, convert to sheet metal, pick a different face, pick a different edge, pick a different edge. Maybe I've got to make this part out of two separate parts. So no big deal. So that's really a process that allows you to go ahead and take any part again and turn it into a sheet metal component. So we'll hide that guy, we'll hide that guy, and now I'm left with a couple of separate sheet metal pieces here. Okay, so that's how that all goes. But again, same form, fit, and function when it comes down to it at the end. Make sure we're staying on time. Oop, I'm going slow. All right, so that is super, super powerful. Miter flange, this is really something where you can create almost any enclosure type shape. This is going to happen on a lot of these boxes out here where you've got a box with electrical pieces in there and then you've got a door that closes over those. There's always a lip, there's always an overlap, and that's the kind of part that you're going to get in something like that. So visually here, let me just open up quick examples here since we're running low on time and we always go over. Is you're looking at a part that's really just a basic sheet metal part. What I've got right here is a simple extrusion. That extrusion is just based on the most basic of sketches, and as a result of what we've got right now, that's going to give us a basic flat pattern, right? Nothing really exotic to that. But if you were to come in here, pick an edge and start a sketch on that edge, which again is a magical thing right here, by picking an edge and starting a sketch on there, it actually creates a plane right there at the end of that, and it creates a sketch for us. And a miter flange is something where you can make some incredibly complex edges just by the way that you sketch things. So I'm going to sketch out, you know, a pretty ugly looking feature here, let's be honest with you, on what we're doing here. I'm not going to do too many with dimensions. But with something like this, what you can do with the sheet metal tool here is create an entire compound flange as a result of this little miter flange tool. Bless you. What it'll do initially is it will put that part in place, and like all other sheet metal features, it's going to give you options to go ahead and change where that radii actually blends off the existing geometry. So if you just want the radius to roll off the edge, or if you want this outside face to be tangent with the existing outside face, those are kind of the points in between that you get as choices there. But what makes this one super powerful is at any point I can incorporate other edges, and where those overlap each other, they're going to go ahead and give you the proper gapping there. This one will get really bad. So look at how it trims that back. Look at how it trims each of these back. And really what's also happening here is this little propagate to tangent button pops up anytime you pick these edges. So if you didn't want to pick them individually, you can just pick one of those and it will just pick the rest of them. But you can see how compound this gets. We'll wait for my preview to pop out. One little sketch creates what's essentially 3 different bends on this, but it automatically trims those in the corner. So what creates basically lips over something that could be a box or a cover that's going to close to this and seal up, you end up with an incredibly compound flat pattern because of how these things all miter to each other in the corner. So we want to build it in 3D, of course, so that it fits in 3D, but we have to manufacture this at the starting point, which is going to be the flat geometry that's there. So miter flange is definitely one that you want to take a look at in more detail. Okay, lofted bends. Well, lofts by nature in SOLIDWORKS are blending of dissimilar cross sections. So what we're talking about with any lofted bend is taking, in a lot of HVAC situations, square to a circle. Now, square to a circle is a ductwork type of a blend, but there is a difference between a bent part here, which is press brake, versus a formed part, which would be over some sort of die shoe or form or hammered or whatever it is. So there's a couple of different ways that this gets controlled. Like regular lofts, you could have a feature like this here, which is just lofting 2 splines together to create a sheet metal part. Now, what's interesting about that also is that there's limitations to that. It's a pretty cool feature to create that kind of a loft, but the reality is it only has the ability to use 2 sketches, and you can't use guide curves. And those are 2 things that to me are pretty well knockouts. What you're doing with something like this, just to kind of give you an idea, is there's a couple of sketches here, and all we're doing in the sheet metal tools is using this one called Lofted Bend. Now when you use a lofted bend, we're blending these 2 sketches, which are just open splines at this particular point. But you have to go ahead and use the formed option, not the bent option. This is too organic for it to have any type of press brake lines that are put in there. What it does give you in this situation is the straightest distance between these 2 sketches, like any loft does, and it does do a flatten, which is actually pretty cool. But geometry on one end and geometry on the other, you don't have that, which a typical loft you would be adding additional profiles and guide curves to create something like that. So it's an interesting thing to be able to use, but for this application, this is kind of an elaborate shape. Yeah, Mike?
Would the flat drawing of that show where each press brake line?
This one does not, no, because it's a formed. And that brings me to this example here, because that's a very important question. When we're looking at something like this is a sheet metal that would be the circle to a square, but we always prep these with a little bit of a gap. That's not a demo trick. We teach that in training because it's sheet metal. It has to be able to open up and close. And when you go ahead and do a lofted bend on what is really decidedly 2 dissimilar profiles, when you go from the circle to a square, see this one I have to do bent. It won't even let me do formed because I've got sharp corners. What this will actually do is it will give you those press brake points, okay? Now, this one here is going to show you each of those not only in the formed mode, but also in the flat pattern, because these are legitimately edges and radii. Okay, so you're going to see each of those. That is also something that as you create these types of features and you're editing or creating the loft in general, each one of these bends, anytime you see a magenta dot, you can action on those individually. If I wanted to take this particular bend here and determine, not chord length, but maybe a number of bends there, then I could go ahead and actually put in more or less depending on how quality I wanted that. And of course, whenever you're talking about facets, the more you have, the more round something gets created with flats. So you'll see that this one edge here is actually a lot more round, even though it's a series of flats, but it's 20 versus 12, so much more round in that respect. The opposite part of that, again, is the formed feature. So now we're talking about something where we've prepped it a little bit for something like this, but not sharp corners in the corner. We've actually prepped it with radii features on something like that. So same operation. Let's go formed on this one. And with any loft, we're just picking these lofts roughly where they're going to bend. So now you don't see those individual bends, right? And what you're basically getting here is a smooth-ish part, I guess, on this one. We did put arcs in there, so you're kind of seeing the facial segments, but if we don't put those arcs in there, then you're not going to see each of those features. All right, let's just do this last part here. I want to talk about this for a second. There is a flattening tool in SOLIDWORKS Professional and Premium that is called Surface Flattening. Sorry, I think it's only Premium. Is that right, Tim? It's only Premium. that does allow you to take any compound selection of faces and flatten them out. It's basically for creating decals. It has some vetting tools for actually doing some calculation stuff. They're going to start doing some drawings and stuff down there in a second here, so I'm going to do this one last one and then turn you guys loose. But this is an interesting thing. So if you do have access to SOLIDWORKS Premium, you can get the flat pattern of pretty much any geometry that you've created. Now, I say that with a little bit of hesitation because we have a third-party product that's called Forming Technologies that is for stamping dies. It's for doing door panels and one-hit type operations with draw beads and binder plates and all kinds of great stuff. But when we're talking about this one here, this is one tool here that's, again, called surface flattening, and it only exists in a premium seat of SOLIDWORKS. But it enables you to go ahead and select a face like this one here, which is actually domed in 2 different directions. So you can see that that is compound in both different ways. There's no flattening of that in a realistic sense. But by grabbing it like this and just selecting the face and then any particular reference edge, we create a flat surface from that feature. Now what generally happens as a result of that is you're going to get a surface that if you right click on actually has a deformation plot that shows you the tension that you get from having a domed in 2 different directions feature flattened. There's a lot of compression that's happening in these areas. And what's really interesting about the tool is the tool addresses that by actually allowing you to deal with that particular feature. I'm going to just delete this feature to show you a second time. We're going to put that in one more time. But what it enables us to do is pick this surface, and I'm going to utilize a couple of little edges that I put in there called hold lines. There's these little blue edges here that I've used to split this face. If you put those in as relief cuts, what it actually does is it allows it to separate the decal where you have those lines. What that essentially does is it takes all the tension off those edges. So now because it's cut there, what you can kind of imagine as this thing relaxes is once it kind of rolls over the face and kind of comes together, those edges come back together as a result of that. So that's why you don't see any red in there, because there's no tension anymore. Once they lay around the face, those edges will kind of end up coming right back to each other. Again, hand puppets is the only way I can do that. So this is a tool that's out there. This is actually literal a surface in the feature too. It's not just an analysis. There's something, you got geometry that you can right click and DXF that bad boy out and be able to go ahead and cut this on a decal cutter or Mylar or something like that. Okay, that's it. You can also import parts from other systems. If they have constant wall thickness, we can unfold them immediately. If they don't, you can actually use thickness analysis, which is in Professional or Premium, to find things like bad radii, delete them, put new fillets in, and then flatten these parts. But you can work with parts from other systems as well. Mike?
When will gauge tables be associated with your material selection?
I don't know.
Okay.
They're still not though, are they?
They are not.
They are not. Okay. My name's Darin, so if you want to send me an email on this, dgrosser@goengineer.com, guys, and I can send you anything on there. So, all right, I appreciate that rapid fire sheet metal. All right, take care. Thank you.